All right. So, guys, I think I shared this with you last time, but let me share it again with you now. So, did I tell you about my AP chemistry experience in high school?
No.
Okay, it's because there wasn't one. So, the high school that I went to did not have any AP classes. But frankly, if you went back and looked at my general chemistry notebook, which I still actually have over there, if you looked at my general chemistry notebook from my regular chemistry class, it's everything that we do in AP. 30 years later, we've just dumbed everything down to the point where general chemistry could be an elementary school class. But all of that to say, guys, they didn't have a second year chemistry class at my high school. So me and a couple of my friends, yeah, I was sort of borderline geeky in addition to being an athlete. Not that those two are mutually exclusive. We went to our chemistry teacher and they said, we'd like to take another year of chemistry. What do you got? And he said, nothing. And we said, come on, you got to have more than that. So he agreed to teach a second year class during his prep period just for the four of us. And so it started out well. We were sort of working our way through a college text. And increasingly over the year, he got busy. He was spending less time with us and more time prepping for his other classes. And finally, by the time Christmas rolled around, he just basically handed us the book and said, have fun with this. I'll write tests. You guys can figure it out from there. We weren't doing any labs, and we were figuring it out all on our own, which actually went surprisingly well until we reached buffers. When we hit buffers about this time, it all just fell apart. None of us understood it. We went to him, said, hey, would you please teach us buffers? We don't get this. He said, sorry, I don't have time for you. And basically it put an end to it. We spent the next really quarter and a half doing nothing. He gave us A's because he felt guilty. But it was sort of the end of it. So guys, frankly, this is the first time in high school where I remember just being confused, going, I have no idea what this is all about. So then I got to college. Frankly, college was just a whirlwind. And then when I started teaching chemistry, we obviously don't go over any of this in general chemistry, which was the first 10 years of my career. And then when I started teaching AP about 17 years ago, this scared me to death because all I had was this memory of, oh crap, this is hard. And then frankly, it made me sort of dig into this to really understand it in order to be able to teach it. And frankly, at that point, I was embarrassed because it's actually not hard at all. If this teacher in my high school had sat down with us for 20 minutes and had any clue what was going on, I think he could have easily taught it to us. It's really not that hard. The math of it gets a little complicated, but guys, the bottom line, the concept is really not that bad. So that's how we're going to treat this. In order to understand buffers, what you first have to understand is something called the common ion effect. That's what we're going to do today. We're not even going to talk about buffers. Today, you're going to learn the common ion effect. And once you really understand the common ion effect, at the end of the day, we're going to say, hey, by the way, guys, everything we just talked about, all those things are buffers. And then we're going to hit stop and you're going to do your homework. Then guys, when we get back after the long weekend, then we're going to go, oh, by the way, those things that we were talking about, those are actually buffers, and let's call them buffers, and let's understand the concept of buffers, and we'll do that on Wednesday, and then we'll do the math of buffers on Friday. You ready to go? Okay, so guys, common ion effect first. You're going to need space to write. You're probably going to need a calculator. Let's remind ourselves of our good friend, Le Chatelier. Oh, baby. But it makes sense, right? We're doing weak acid-base systems. Weak acid-base systems reach equilibrium. And who knows more about equilibrium than Le Chatelier? Nobody. So guys, what does Le Chatelier say about equilibrium systems? Well, he says that they respond to stress by trying to undo the stress that you're doing. But we're going to talk about this specific to taking a system that is at equilibrium and adding a product to it. So guys, I asked the question not hypothetically. Whether you write it down or not really doesn't matter. But if you don't want to write, I don't have my writing stuff. This is okay. That's okay. Okay. So guys, if you don't want to write down the sentence, that's fine. I forgot to unfreeze. What the question is actually asking you is this. If you've got reactant 1 plus reactant 2 in equilibrium with product 1 and product 2, and if you come along and increase the concentration of either one of these products, well, that's deceiving. It's not both. So if you come along and let's say we increase the concentration of product 1, we just grab the beaker where this equilibrium exists and we dump in whatever product 1 is, and we increase the concentration of product 1, what direction will that shift the equilibrium? To the left, yeah? So notice I didn't say to the left, right? To the left, yeah? Okay, so it goes, these are things that you do when you get better at teaching, because if you had said to the left, right, everybody, okay. So it goes to the left, yeah? Okay, and so guys, the idea is that these will go up, shifting the equilibrium to the left. A little bit of review. We understand that adding this increases the concentration, which increases the rate of the reverse reaction because there's more collisions of products, drives the equilibrium that way. You guys good on the, okay. So guys, with that said then, let's make this real and let's do some chemistry. So guys, consider the dissociation of acetic acid, which is simply this. Because here's what we're going to do. And we're going to talk about, I don't even think you need to write this down. Let's do this conceptually first. So guys, acetic acid dissociates into acetate ion and protons. Guys, why is the acetate ion first? Doesn't matter, right? But we said we're going to put the conjugate base first. You're going to find out why on Wednesday. Just trust me for now. Now, guys, here's the question. What would it do if we dumped in acetate ion? So if we took this equilibrium right here, and if we increase the concentration of acetate, again, given the first question we talked about, you should know the answer. What is that going to do to the equilibrium? Shift it to the left. Okay, so guys, if that's true, the question then is this. How could we do this? So guys, if we've got a beaker, and you guys all understand, well, I should be careful. What is acetic acid? Vinegar. So in a bucket of vinegar, you've got all three of these things, right? You've got unprotonated acetic acid, you've got acetate ion, you've got sodium ion. So guys, where are the acetate ion and the hydrogen ions? I said sodium ion, sorry, hydrogen ion. Where are the ions? In solution. Where is the unprotonated acetic acid? Also in solution. All of this is dissolved. It's just that some of it's not protonated. Now guys, do you remember the numbers, just frame of reference? If this is what did we do, 0.1 molar? If this is a 0.1 molar solution, how much of that's not protonated? Wasn't it like 90? Wasn't it like 96% of this is unprotonated? It's like 4% proton. It doesn't really matter. But guys, we understand that more than 90% of this is hanging out in this form, and only about 5-ish% is like this. You guys good? Okay. Now guys, here's the question. So what we just said is if we increase the concentration of acetate ion, what is that going to do to the amount of acetic acid that's unprotonated? It's going to go up. So the question is this: how do we do that? If we grab a bottle of vinegar and if we want to increase the concentration of acetate, if we want to increase the concentration of acetate, what could we do to our bucket of vinegar to make that happen? Right, but how do we do that? What could we fit? If you go in the stock room, where would you go in those cabinets to grab something that you could do this? No, but we're not trying to, we're trying to make this go up directly. But no, because that's this, and it wouldn't change the amount of it that's dissociated. Where are you going to find acetate ion? There is not a bottle of acetate ion in lab. Where do you find it? In an acetate salt, right? Guys, acetate is an anion, and if you want to add acetate, what you're going to add is an acetate salt. Now, I would suggest to you that sodium acetate would be a better choice than copper acetate. Why would sodium acetate be a better choice than copper acetate? Just use our word. It's what? No, use our word. It's worthless, right? Guys, sodium acetate is a worthless conjugate acid, so it's not going to do any chemistry. If you were to grab copper acetate, which we also have, it's a really pretty green color. Guys, if you were to grab copper acetate, the copper is going to do chemistry, which could mess up the chemistry you're trying to do. So when you grab salts, in order to create these common ion effect, which is what we'll call this in a minute, system, you will always grab salts where the ion that you don't care about is worthless. You're going to be doing this in lab. Does this make sense? Okay, so guys, the idea then is this, that we could add something like sodium acetate, lithium acetate, rubidium acetate, cesium, calcium, those. We're going to add a group 1 or heavy group 2 metal acetate salt, and then when this breaks apart into water, we've got sodiums, those are worthless, we've got acetates, those are what we care about, and as we add that acetate, guys, that's what it does. It increases the concentration of acetate, which drives this equilibrium to the left. You get the idea? Just Le Chatelier's principle, right? You guys okay? All right. So now, guys, here's the question. What does doing that have on the strength of the weak acid? Let me put this back in context for you. So, guys, here's the... that's too sloppy, isn't it? Let me just start over. So, guys, here's the idea. You've got your acetic acid. The acetic acid is broken down into acetate ion and hydrogen ion, and that thing reaches equilibrium. We said that it's about 5% protonated, right? Somewhere thereabouts. So now what we're saying is this. We come along and we dump in some sodium acetate. What does the sodium do? Nothing. What does the acetate do? Well, the acetate drives up the concentration of acetate ion. When that happens, which direction does it switch the equilibrium? To the left. And so as it goes this way, this goes up. What happens to the amount of protons in water? It goes down, right? Same side does the opposite, opposite does the same. So if this goes up, this goes down, what does that do to the strength of the acid? Weakens it. Does that make sense? That as we add this acetate ion, it drives the equilibrium to the left. There's less protonated hydrogens. Excuse me, it weakens the acid. Yeah, so just a second, Brad. So the strength, when we say strength of an acid, we're talking about the extent to which it protonates. Strong acids do it completely. Weak acids were on that sliding scale represented by Ka. The pH would go up. Think about it. If it's less acidic, it goes up. The pH would change, but the pH would go up. Yeah. You knew what you were saying. Go ahead.
So I understand the entire explanation principle.
Okay.
But if we're increasing the amount of reaction that's happening to our acetic acid, wouldn't that give us more? So we add.
Right. So we add this. This goes up. Equilibrium shifts left. This goes down. This goes up.
Yes. And now, since there's more of that stuff actually reacting.
It can't, because we've reestablished a new equilibrium where there's more of this and less of that. That's the whole idea behind Le Chatelier's principle. It doesn't go back to where it came from. When we add this, this goes up, this goes down, it reestablishes a new equilibrium where there's more of this and less of that. If it went back to where it came from, we wouldn't need Le Chatelier's principle because nothing changes. Do you know what I'm saying? You guys good on the concepts? Okay. So let's answer Mark's question here just really quickly. What would that do to pH? If the acid is weaker, the pH goes up, right? So guys, here's the trick. That's it. You now understand the common ion effect. You're done. That's what Mr. Cathan, my high school chemistry teacher, was either unwilling or unable to teach us. It's called the common ion effect. So this you definitely want to write down. So guys, think about it, and maybe, you know, I won't, but maybe I should. That's the important idea, the common ion effect. Guys, in order for you to have any chance of success in chapter 17, because all of chapter 17 is about the common ion effect, guys, you got to understand this. So first of all, take the name and figure out where it comes from. Why do we call this phenomenon the common ion effect? Because we're adding an ion in common, right? The idea is that we've got this weak acid, in this case acetic acid, and what we did is we came along and we added sodium acetate. Why sodium acetate? Because that salt has an ion in common with the weak acid. So we call it the common ion effect. Does that make sense? So, guys, to lay this all out for you then, the common ion effect simply says this. The dissociation, think about the word, it means to break apart. The dissociation of a weak electrolyte, in our example acetic acid, is decreased by adding to the solution a strong electrolyte. What does that mean? It means it completely breaks apart. That's our salt. That's our sodium acetate in our example. By adding a solution of a strong electrolyte that has an ion in common with the weak electrolyte. Yeah. A substance that creates ions in solution. So salt, table salt, is an electrolyte because when it dissolves it breaks into sodiums and chlorines. Sugar is a non-electrolyte because while it dissolves it doesn't create ions. Are you? Well, but realize that acids and bases are electrolytes. Right. Yeah, go ahead. Yeah, so let me find a little space here. Yeah, so bases do the same thing. So for example, if you had NH3 reacting in water to form NH4 plus and OH minus, and if we wanted to common ion effect this thing, we would need to add a salt. This is an interesting question. Maybe I should make this a part of the notes. Guys, here's the question. What salt would we add? A salt of what substance? The ammonium. So we would add a salt of ammonium. So ammonium would be our positive ion, and then somebody already said it, we would want our negative ion to be the child of what? A strong acid. So we could add ammonium chloride, we could add ammonium nitrate, which is lawn fertilizer, we could add ammonium iodide, ammonium bromide, or any of the, but we would need to add an ammonium salt to do this with this particular example as a base. Yeah. Were you talking about the idea that some things that we think of being non-soluble actually dissolve a little? We did talk about that, and we're going to talk about that in chapter 17. like silver chloride, sort of one of our classic ion or salts that doesn't dissolve in water, even though we think it should because it's got chlorine in it. Turns out silver chloride does dissolve a little. It's minute, but we're going to look at that at the end of this chapter.
I think it was, you said that we were just going to pretend all
Yes, or don't dissolve. Yes. Oh, yeah, and that's all the same conversation. So we said either salts dissolve completely or don't dissolve at all. Now in chapter 17, later on in this unit, we're going to acknowledge that the salts that we have always said don't dissolve at all just dissolve so little that we say they don't dissolve at all. In fact, they dissolve a little bit. Yeah. All right, you guys good on common ion effect? You guys good? Let's do some ice boxes. Here we go. So guys, what is the pH of a 0.3 molar acetic acid solution? You got 5 minutes. Go. Oh, by the way, sorry. The Ka of acetic acid, frighteningly, I know it, 1.8 times 10 to the negative fifth. Interestingly, that's also the Kb of ammonia. Coincidence?
I think not.
Nah, it is. So guys, what is the K? And by the way, you want to, don't chicken scratch this. You want to organize this, because we're actually going to come back, and the icebox that you're about to create, we're going to come back and recreate. So you want it well done so that you have a foundation upon which you can build the next thing we're going to do. No, negative 3. So, yeah, sorry, yes, it's beyond it. So negative 4 is our be careful point. Negative 3 is never. Negative 5 and below is fine. Negative 4 is be careful. So yeah, this is A-okay. Even if it was like 9 times 10 to the negative fifth, you'd still be fine. That's where you got it, yeah. But again, I've never seen them throw that at you on the test. So guys, I know that I said earlier that we're going to be sort of guarded about this idea of calling these things buffers. We are going to talk buffers. We're not going to get into it real deep, but we will. You'll see. We're going to skip across the surface of it today. I guess what I should have said better is we're not going to start by talking about buffers. We're going to start by talking about common ion effect. So let me catch up with you. You should be pretty close to done. So CH3COOH. No, I didn't like that. How'd I do?
You did perfect. Yeah.
Guys okay?
I'd say 100% on the test question.
Okay. So, guys, this is all chapter 16, right? Questions, thoughts, concerns, things we need to talk about. Yeah. To be honest with you, I don't remember. Yeah, so here's the thing. And guys, we're going to talk about significant digits on the AP test when we get closer. We have never talked about significant digit rules for logarithms. It turns out that the significant digit rules for logarithms are not as simple as you would think. And to be honest with you, I haven't spent the time to memorize them because I'm going to show you how to just fudge it on the AP test. But don't quote me on this, but I think the rule is the number of decimal places in the base of the number in scientific notation is equal to the number of significant digits in the logarithm.
So that should be 2.6 then, technically.
I don't even remember. Somewhere in our textbook, it talks about the rules. The bottom line is, what I do is this. However many digits are here, that's what I do there, understanding that technically it's wrong, but it will get you credit on the AP test, if your numbers are right. So, yeah. Go ahead, Rebecca. You guys okay? Okay. So, guys, I'm getting the sense that either because you're confident in this or because it's the day before a long weekend, we're sort of getting a little buzzy right now. Because we got to focus, because we're about to, I know this is chapter 16. I know that you understand this well, or you should. But guys, please don't lose sight of what we're trying to accomplish here, because this is headed somewhere new. So now let's take this somewhere new. So guys, let's remind ourselves what we just established. So we now know that in a 0.3 molar solution of this acetic acid, that this solution has a pH of 2.63, and we're settled on that. Are we good? Okay. Now, guys, this is where we're headed with this. What is the pH of this solution? Still a 0.3 molar acetic acid solution, if now we also add to that solution enough sodium acetate to make it 0.3 molar in sodium acetate as well. We're going to do this one together, skip a couple lines, and put it right below the calculation you just did. So guys, this one goes like this. We've got CH3, COOH. And we're going to icebox this. But guys, before we even dig into the icebox, let's talk about this conceptually first to make sure that you understand where this is headed. So I know we've already read over the setup for the problem. But guys, what does this have to do with what we're currently in the process of learning? Well, and that's where I wanted to go with this. But do you all see that this is a question where we're going to be studying the common ion effect mathematically? So we've got acetic acid, which is a source of acetate ion, and now we're adding sodium acetate. We've talked about this conceptually. Now we'll do it mathematically. But Brendan, that's where I wanted to get us. Are we okay with the idea that because we are now including a common ion, the pH should go up because this acid will be weakened? Okay, so now let's do the math. So guys, this is what we did before. We know that this is 0.30 molar. Now, what about the other side of the equilibrium? Well, it was that we would go 0 and we would go 0. But that is no longer the case. Which one of these, and you got to drop the noises, guys, stay focused. Which one of these is no longer 0? The acetate ion. Guys, this is now 0.3 molar, and this is 0. Yeah?
On the AP test, would we need to include sodium in the
No.
equation and just cross it
It's not even there. Nope, you just like this. Nope. It's a spectator, so you don't have. Everything on the AP test is always written as net ionic equations, no spectators. Yep. Okay, so now guys, it's just a new starting point, right? But now when this goes to equilibrium, this will go down by x, this will go up by x, this will go up by x. Now when we go on from there, we're going to have 0.30 minus x, 0.30 plus x, and x. Now guys, let's continue as we've done before. Ka is equal to acetate ion, hydrogen ion, and unprotonated acetic acid. And now we've got 1.8 times 10 to the negative fifth, because this is still acetic acid, is equal to 0.30 plus x times x, all that divided by 0.30 minus x. Now guys, at this point in the previous solution, we did the approximately equal to, and what did we get rid of? The minus x. We got rid of this. And guys, let's talk. Why is it we were able to get rid of that minus x? First of all, let's talk about it numerically. What allowed it? 10 times, this is times 10 to the negative fifth, Ka is small. But now let's talk about it conceptually. Because Ka is small, why does it make it appropriate to get rid of x? Because it's insignificant compared to what? To the 0.3 mole. Guys, let's go back to the icebox. The idea is this. We can get rid of this minus x. And what does the minus x represent? The amount of the acetic acid that falls apart. So we can get rid of the minus x because it's insignificant compared to the overall starting concentration. Do you see where this is headed? Guys, if this, the amount of acetic acid that falls apart, is insignificant compared to 0.3 molar, what about that x? What does this x represent? The amount of acetate ion that is formed from the falling apart of the acetic acid. So the amount that this goes down is equal to the amount that this goes up, and this amount that this goes up will also be insignificant compared to this 0.3 molar, so we can get rid of both of them. Now look what this shrinks down to. This now, well, do you see it? Yeah, guys, look at what else happens. Our 0.3s drop out, and we end up with x. And it's not only nice, this is going to become very important in about 90 seconds. So guys, let's finish this then. Because now, oops, that's not what I wanted to do. Now we know our pH. Because pH is equal to the negative log of hydrogen ion is equal to the negative log of 1.8 times 10 to the negative fifth is equal to 4.74. So guys, let's have the conversation. Did this do what we expected this to do? Yeah. pH went up, right? We started at a pH of 2.63. I love that I can switch between those. Started at a pH of 2.63, went up to a pH of 4.74. Guys, how many times weaker is this than the previous solution? Let's look at the numbers. This was 2.6. This is 4.7. How many times weaker is our common ion solution? 100 times weaker. The difference between about 2.6 and 4.7, a pH change of about 2, is a concentration change of about 100. So this is now 100 times weaker. Do you understand the idea, the chemistry, and everything that we just did? Now, guys, watch this. And you're going to want to include this in your notes. This is going to be a lifesaver for you. Guys, let's go back here to the canceling that we did right in this area. Guys, why did we cancel what allowed us to cancel these x's? They're insignificant compared to the initial concentrations. Once those x's canceled, what allowed us to cancel the 0.3s? They're the same number, but what do they represent? Well, they represent the molarities of what? The acid, the weak acid, and the conjugate salt. But guys, look at what happened. Follow the math. When those dropped out, we were left with X. So that means that X, which is the hydrogen ion concentration, was equal to what? Ka, right? So our hydrogen ion concentration became Ka. So when we came down here and took the negative log of hydrogen ion concentration, what were we actually taking the negative log of? Ka, but what is the negative log of anything called? Well, that's a P, right? So functionally what we actually did down here was pKa. Do you get it? So guys, here's what that means. When this equals this, then pH is equal to pKa. You want to put that in your notes. Not yet. Guys, it's critical that you understand that deep thought. That when the molarity of the weak acid and the conjugate base, when those the conjugate base salt, when those molarities are the same, then pH is equal to pKa. That will save your bacon on the AP test. So guys, once again, just a second. When the concentrations of the weak electrolyte, in this case acetic acid, and the conjugate base salt, in this case sodium acetate, when those concentrations are the same, pH is pKa. Go ahead. No, never. Go ahead. Yeah. That's a good question. No, that's a good question. Yes. You know what, Mark, and Rebecca, because you're now in the conversation as well, I'm not comfortable saying yes. So did you guys hear Mark's question? He said, because we've just established this rule, can we just say pH is pKa, or do we need to icebox it? And again, my answer to you is I'm not comfortable saying yes. What I'll have to do is go back and look at the solution sets to questions where this is the case. But general, we can say this. You could not do that without some sort of explanation, which, Rebecca, is what I think you were getting at. At the very least, you would have to say, because this molarity is equal to this molarity, in this case the point, because these molarities are the same, then pH is equal to pKa, then do the math. I think you would be okay with that, but that said, you're never wrong doing the icebox. But I would be really... I'm 90% comfortable saying if you can write out that statement that says molarities are the same, therefore pH is pKa, then do the math. I think you'd be okay. But let me make sure before I say yes. Go ahead, Matt.
Yeah, isn't this the only case when Ka is really small?
Yes.
Yeah.
And that's also the case that none of this works, because if Ka is bigger than 10 to the negative third, then you can't even get rid of the x's, and then all of it falls apart. Yeah, just a minute. Okay, yeah, so, but again, I can't remember in my memory, which goes back to 99, an example. That's crazy. I started doing this in 99. I can't remember an example of a question on the AP test where Ka was small enough that you couldn't disregard the x.
That equation that equation.
Which equation? Sure, but it doesn't say pH is equal to pKa, does it?
Yeah, that's true.
No, I mean, yeah, it gives us the pKa.
Well, it sort of does. You have pH equals pKa plus log of concentration of A minus over H.
Oh, yeah, no, that's, oh my gosh. Yeah, and I thought they got rid of that equation.
I don't know. This is just.
They know, I know. What? Holy smokes. What year is this? So that equation that you just referenced, Brandon, the second one from the bottom that has absolutely nothing to do with what we're doing right now, is it? No, it's okay. It's actually called the Henderson-Hasselbalch equation, and they took that away from us. And it looks like it might be back. I don't want to look now, but
Is this a current?
that's what I need to check on. I'm not sure. I'll check and see. But it looks like they brought Henderson-Hasselbalch back, which would be really unfortunate because it keeps you from learning stuff. Okay, so guys, you good? Okay, so let's go back to where we were. We understand this idea of pH is pKa if the concentrations are equal. But guys, more importantly right now, we understand this idea, that in its uncommon ion effect form, Rebecca, make sure you're tracking with me. In its uncommon ion effect form, this had a pH of 2.63. We did the math. Now we see that when we add the common ion, the pH goes up. That's the common ion effect, right? You good? Okay, because guys, here's the deal. This is a buffer.
Really?
What you just built is a buffer. When you took that weak acid and when you added a conjugate base salt, common ion effect, right? When you did that mathematically, what you actually created was a buffer. This is a buffer. This is not a buffer. What's missing? The conjugate ion salt. But when you take a weak electrolyte, a weak acid, and add to it a common ion salt, what you have done is created a buffer. So guys, we are going to talk now briefly and conceptually about what a buffer does. So guys, first of all, let's make sure we're clear on this. So this second solution was a buffer, and you've already written this down. When we have equal molar concentrations of acid and conjugate base, then pH is equal to pKa. You good on that? Okay. Now guys, do this with me. Let's talk superficially about buffers. So what is a buffer? Write this down. What is a buffer? Well, guys, I think you've probably heard of the term buffer. Well, maybe you haven't. But when I think of the word buffer, I think of padding. So you've got something that decreases an impact, if you will. You've got a buffer zone. They talk about that in driver's ed. You've got a buffer is a region or a system or a situation that decreases the impact of something that could otherwise be a problem. So in the context of acids and bases, buffers are solutions that resist changes in pH. And Joel, I see you in just a second. So how do we make buffers? Well, first of all, it's an acid or a base, but it has to be weak. It is a weak acid or a weak base that is mixed with a conjugate salt. But guys, when you hear that, your brain should immediately go, common ion effect, because that's what we're talking about. And guys, generally, when we talk about buffers and the buffers that we'll talk about in lab, we will traditionally be buffering weak acids. You can just as easily make them out of weak bases. It's just we have a much larger selection of weak acids. So those are the things that we tend to buffer. And Joel, I know you have a question. Let me add one more point and then we'll talk. So guys, this then is the thought. What do buffers do? Well guys, what they do is they function by absorbing, like a sponge, hydrogen ion and or hydroxide ion. And as they absorb this hydrogen or hydroxide ion, they do it without a significant change in pH. So guys, that's what buffers are. Buffers are solutions that create a sponge, if you will, that are resistant to pH change. And in order to create buffers, it's simply the common ion effect. So let's let everybody get caught up in these notes, because we've only got one more page to look at. So let's get caught up, let's answer questions, let's play with this a little bit, and then we're going to call it a day. You're going to have time to work on your homework, and then we're going to get back next time and really dig into the chemistry of how these things work. Are you guys caught up enough that we can all talk about questions? Is that okay? Go ahead, Joel.
Yeah.
Perfect. Rachel, were you headed somewhere with us?
I was just clarifying that the buffer refers to the entire solution, not just the...
That's absolutely, yeah. So if I could do, I don't even know if I can do this. Let me try. So yes, so what we would say is this is not a buffer. So if you picture what we're talking about here, this is a jug of vinegar, okay? That is not a buffer. This is a buffer. So what we're really talking about is a beaker that started as a jug of vinegar that we added sodium acetate to. And as soon as we add that sodium acetate to the vinegar, it is now a buffer. And so the way that we would say that is we have buffered the vinegar. And adding that sodium acetate buffers the vinegar, creating a buffered solution, and the whole system is the buffer.
So then what's special about it is that now that we have the buffer, if we were to add anything to it, it wouldn't change.
Exactly. So as soon as we've added the sodium acetate, and we're about to look at why, but as soon as we add the sodium acetate to the vinegar, it's now buffered. And we could dump hydrochloric acid into that, and the pH wouldn't change much. We could dump sodium hydroxide into it, the pH wouldn't change much. Yep, that's exactly right. Go ahead. You good? Go ahead.
So you said and or
Yeah.
hydrogen. So we have like something like an amphoteric buffer.
All buffers are amphoteric.
Well,
Yeah.
Like in a sense that it can accept both hydroxide.
No, that's what I'm saying. They're all amphoteric, and we're about to look at why. So a buffer wouldn't be a buffer if it couldn't absorb both. So by definition, a buffer has to be something that can absorb hydrogen or absorb hydroxide and soak up, if you will, either one of those without changing pH much. Yeah, and the chemistry is cool about how this works, and we're about to look at it. Go ahead.
So, because that once we added that conjugate ion
Yeah.
to salt,
Mm-hmm.
that's the main cause of this is now a buffer.
That is what makes it. It's not the main cause. It is the cause. That's how you make a buffer, is take a weak electrolyte, in this case acetic acid, add that common ion, it's a buffer.
So, could we go further and state that the common ion effect, that buffering is a consequence of the common ion effect?
Only if you're doing the common ion effect with acids and bases. Understand, the common ion effect can happen to any weak solution. And we're going to talk about the common ion effect. This is where Talmage was going. We're going to talk about the common ion effect with slightly soluble salts later. So the common ion effect is what creates buffers, but buffers are only, systems are only thought of as buffers if it's an acid or base buffer. We can common ion effect anything that reaches equilibrium, but if it's an acid or base, it makes a buffer. Go ahead.
So the process of buffering
Yes.
solution change the pH.
It does.
So
Ooh, keep going, Em. And guys, don't miss this. Rebecca, focus. What does this do? Go.
I was just asking, is buffering making it closer to pH of 7, or does it keep it neutral?
Good question. And so here's the first thing, and I'm glad that you said this. So let's talk about it. Guys, did you see what Ammon said? That creating the buffer changed the pH, right? Think about that. This thing started at 2.63, and when we buffered it, it went up to 4.74. So what you're saying is correct. Taking a weak electrolyte, be it an acid or a base, buffering it pushes it towards 7. So now, how do we know where the pH will end up when we buffer it? And guys, that's the beauty of this idea that pH is equal to pKa. So what you do when you're trying to build a buffer is you say to yourself, all right, I want a buffer that's around pH 4.75. So what you do is you grab a Ka table and you find a weak acid that has a Ka value of about, or a pKa value of about 4.75. Then all you got to do is add equal moles of each, and there's your pH. Did that make sense? So guys, say that you, let me do a different example. Say that you want a buffer at pH 4.5. Well, clearly acetic acid's not going to be a great choice because when we add equal molar amounts, it goes to 4.74. So what do? Well, we grab a pKa table and we find a weak acid with a pKa of 4.5. Then all you got to do is take that weak acid, find its conjugate base salts, add equal molar amounts, and you just hit pKa for its pH. Go ahead. Why what? So, oh my gosh, no. So I don't even know where to begin. There's so many. So as a laboratory chemist, laboratory biochemist, every single reaction that takes place in our bodies, in any living system, is always taking place in the presence of acids and bases because we're made of water. And so when you're trying to replicate biological processes outside of the body, you've got to be able to not only create the pH where that system can actually work, but you've got to keep it at that pH or it stops working. So then when you take that back inside the body, our bodies are huge buffers. Like if you draw your blood, my blood, anybody's blood in this room, our blood will all of us will have the same pH within about 1,000th of a pH step. And if any of them change by more than 1 or 2 hundredths of a pH step, we die. It's called acidosis. So our bodies are these amazingly well-buffered systems. And it's actually really cool because one of the predominant buffers inside your blood is actually carbonic acid. Carbonic acid is just carbon dioxide dissolved in water. And your blood is actually buffered by a carbonic acid sodium carbonate buffering system. And guys, it turns out that if that buffering system starts to break down even a little bit, you're done. But the problem is, are you guys interested in this or should I just stop? So the problem is this, so the buffer that works in our bodies is carbon dioxide plus, carbon dioxide plus water reaches equilibrium with carbonic acid. And then this and it actually goes both ways, so maybe I should have written, but it's a so the buffer is actually, and I won't do this in, it's a carbonic acid sodium, not sodium carbonate, bicarbonate, sodium carbonate. So that's the buffer that exists inside your blood. But the problem is that the amount of carbonic acid in your blood is actually a function of the amount of carbon dioxide that's dissolved in your blood. So guys, how does our body maintain this equilibrium so that the pH of our blood doesn't change? Well, it creates a buffer, but that buffer can be thrown out of whack if we get too much carbon dioxide in our blood. So guys, how does our body get rid of carbon dioxide? You breathe faster. So guys, I don't know if you understand this or not, but do you know how your respiration rate is moderated by your body? And you understand that this is both, what's it called when you can control it or not? Unlike your heartbeat, which just beats, you can't make your heart, you can't go, okay. Voluntary and involuntary. So guys, understand that your respiration rates are voluntary and involuntary, right? You go, and you can breathe faster, but if you're exercising, your body will involuntarily increase its respiration rate. How does it know? There's actually a gland in the base of your brain that monitors the pH of your blood. And when your blood becomes too acidic because you've got too much carbon dioxide dissolved in your blood, it automatically increases your respiration rate to get that carbon dioxide out of your blood in order to bring your, to drop the, or to increase the pH of your blood. Yeah.
So, I mean, it's probably like crazy, but just got some curious about that detector there. Like,
Yeah.
are we, I mean, how many, like, sig figs is that accurate to?
I don't know. Yeah, I've never run the math. You'd have to, but look it up. Yeah, look it up. It's cool. So guys, let's finish with this. This is how we're going to wrap up the day. Write this down with me, big. Think icebox big. This is how we're going to finish the day. And guys, what I'm going to do now is I'm going to explain to you how a buffer works. Jake came up with this important idea that a buffer, he used the word amphoteric, which isn't quite right, but I understand what he's thinking. Because we've got this idea that for a buffer to be a buffer, it has to not only be able to absorb acids, but it also has to be able to absorb bases in such a way that the pH doesn't change. So first of all, let's summarize what we learned today. This is just vinegar, right? Isn't a buffer. It is not. So what do we need to do it in order to buffer it? Add sodium acetate or some other common ion salt. Now guys, the idea. When that happens, let's go blue. When that happens, let me say that the third time. When that happens, I love that you guys think that's funny. So let's see if I can, was it this? Yeah. Okay, now I'm back. Okay, so guys, when this happens, remember what that does. We are dumping in some acetate ion, right? And when we do, it shifts the equilibrium in which direction? And we end up with some more of that being formed. So now what we have is relatively high concentrations of both of these. That's our buffer. You good on that? Okay. Now guys, this. Fundamentally, what do buffers do? And maybe a better way to ask it is, what do buffers not do? Change pH, right? If you have a system that is a buffer, as we do now because we've added the sodium acetate, if you have a system that is buffered, it doesn't change pH very much. When you do what? Hit it with an acid or a base. Do you understand the concept of a buffer? Okay, now this. Guys, where, and I kind of gave it away, where on the board do we see pH? The hydrogen, right? Guys, this is pH right here. So, if we are saying, and we are, that the pH is not going to change very much, when we say the pH is not changing, in the chemistry, what's not changing? The concentration of the hydrogen ion, which I put in blue. Okay, so guys, with all of that said, do this with me. What does this look like? Don't write this down, but here's what we understand. We got a bucket, right? And in this bucket was our vinegar, and to that vinegar we added some acetate ion, and we've got our hydrogen ion, and that's our buffer. And now here's what we're going to do. Now that we've got our buffer, we added our sodium acetate, as Talmadge pointed out. Don't worry about the sodium. Now we've got our buffer, and it's all set up, and it's in a bucket. So what are we going to do to this buffer? Well, the first thing we're going to do is we're going to dump in a strong acid, hydrochloric acid. What's going to happen to the pH of the buffer? Not much. Then what we're going to do is we're going to reset the buffer. We're going to pretend we're going to start over. And then we're going to dump in some sodium hydroxide, a strong base. What's going to happen to the pH of the buffer? Not much. Now guys, some of you may be wondering, okay, we're going to add strong acids and we're going to add strong bases. What if we added weak acids and weak bases? You don't have to worry about that in this class. All that you need to worry about is the buffer and how it reacts to the addition of strong acids and weak acids, okay? So guys, with that said, strong acids and strong bases. There we go. So guys, let's do this first. HCl, which is the spectator, the H or the Cl? Cl. So do this with me, write it right here. Here's our H. This is the addition of an acid to a buffer. And guys, I'm going to get rid of these arrows because they're distracting. Okay, so guys, when we add hydrogen ion, strong acid, right? Would it be helpful if we put the chlorine here sort of in parentheses? Guys, when we add hydrogen ion, what chemistry is going to take place? What will the hydrogen ion grab a hold of? There is no OH. What does the hydrogen grab a hold of? Hydrogen's negative. What's it going to grab a hold of? This. The hydrogen, did I say negative? The hydrogen is positive. It grabs a hold of the negative acetate. What does that make? Makes this. What happened to that? Nothing. Do you see what happens, guys? When you have a buffered system and when you dump in hydrogen ion, the acetate ion attacks the hydrogen ion and ties it up as acetic acid. And because this additional hydrogen ion is being tied up as acetic acid, the pH doesn't change because the hydrogen ion that's being dumped in there doesn't increase the concentration of hydrogen ion, it increases the concentration of acetic acid. Does that make sense? Okay, now guys, we got to talk about the one additional layer. Functionally, what this does is it increases the concentration of this, right? What does Le Chatelier's principle then say is going to happen? This is going to shift a little bit to the right, and it will make a little bit more hydrogen ion, like 5% more. Because remember, acetic acid doesn't break down much. So guys, understand, the pH will drop a little bit. It will become a little acidic. But guys, it's like for every 100 of these that we dump in, they get converted to this, and then like 5 of them fall apart. Instead of all 100 of them just being unleashed in there as hydrogen ion and the pH going through the floor. Do you get the idea? Okay, so now guys, I'm not going to I'll erase this. So let's hit the reset button now, and actually I'll erase this as well. Let's hit the reset button, and now, and this is where this gets cool, now let's talk about the addition of NaOH. So our buffer is back to reset, as if we'd never added any hydrogen. We're starting all over. Sodium hydroxide, which is the spectator? Sodium. So when we add a base, functionally what we're adding is hydroxide. So, what chemistry is going to take place when we add the base? What will the hydroxide attack? It's going to go this way. What will the hydroxide pull off of the acetic acid? A hydrogen, turning this into this, and what is the other product? Water. But it doesn't make any free hydroxide. So guys, when we add sodium hydroxide to this buffer, the sodium hydroxide attacks all of the unprotonated acetic acid that's bobbing around in there. The hydroxide and this hydrogen get together and make water, and then acetate ion is formed. Do you see it? Now hold on. Now, what is this then eventually going to do? Well, what's that going to do to the concentration of acetate ion? It'll go up, and to restore equilibrium, the equilibrium will go back to the left a little bit, and the amount of hydrogen will go down a little bit, so the pH will go up a little bit. But guys, this is how this buffer responds to the addition of hydroxide. The acetic acid reacts with the hydroxide ion, making water and acetate ion, and all the while, this again does not change, so pH doesn't change, realizing it does change a little bit in the end because the equilibrium reestablishes itself, shifting to the left. Go ahead.
Why do you say that it will take the H off of the CH0 instead of the hydrogen ions? Right.
Because the way that this works is that we understand that these hydrogen ions are really not there, right? Where are they? They're bonded with water to form hydronium, and those are easier to steal. Yep. Yeah. Yeah, and that's a great question. But the idea is just that hydroxide will steal hydrogens from whoever will give them up more readily, and that would be the acetic acid. Yeah, and I may show you this video where they actually talk about that, and they go through all the chemistry, and they talk about the strongest acid and the strongest base reacted, but that's why. What do you think, y'all? Good? Okay. So, guys, that was a good day. What we're going to do is we're going to stop here, and you're going to look at some homework that covers the concepts of this. When we get back together after the weekend, we're going to spend more time thinking and talking about this chemistry, and then we're also going to talk about the capacity of a buffer, the pH of a buffer, and what happens when buffers break. Then on Friday, we'll do the math of all of this. And guess what you're going to learn how to do? iRace boxes. Not ice boxes. It is a new iteration of the ice box called an iRace box. Oh, baby. Here's your homework.